So hello everyone, welcome. So today's speaker is Sebastian Haney from Columbia University. So you can read this title in the slides. So please, Sebastian.
Um, okay, yeah, thank you for the introduction and for inviting me to speak here. So I guess the purpose of the talk today is going to be to discuss a definition of the open Gromov-Witten invariants involving infinity inner products and, I guess like more specifically, some kind of like or like strong proper Calabi-Yau structures on the Fukaya category. Okay, so the geometric situation that we'll be in today is that we will consider a closed symplectic manifold M equipped with an omega tame almost complex structure J. And then we'll also consider a closed Lagrangian submanifold in L or in M, denoted by L. And for technical reasons, we will want to assume that it's spin and oriented. Um, Okay. And so in this setting, the genus zero open Gromov-Witten invariants of M and L should count J-holomorphic disks in M with boundary on L. So there's kind of some, I guess, like relative generalization of the idea of a closed genus zero Gromov-Witten invariant. And just for the record, what I mean by J-holomorphic, right, like what I explicitly mean by the sort of object is that I consider maps from the disk to M, which sends the boundary of the disk to L, such that the pseudoholomorphic curve equation is satisfied. So here, little j denotes the standard almost complex structure on the unit disk in C2. And like big J is the almost complex structure on M. Um, Okay, so you would right, so you would naively like to just try to count all disks like this, and so really what that should mean is you should consider like the moduli space of J holomorphic disks with boundary on L, and then then you should consider some kind of Gromov compactification of this thing, right, and then but the issue with doing that is that the Gromov compactifications of moduli spaces of pseudoholomorphic disks have boundary, which is kind of something that you don't see in the closed case. So, and they're kind of two kind of like codimension one nodal configurations that you can see in these moduli spaces. So, on one hand, if you have say a family of disks like this, as you approach the boundary, you can kind of see them break off into some nodal configurations. So, there's like two disks intersecting at each other at a point on the boundary. And then something you can also see is that the boundary of a disk can sort of just collapse and give you a smooth holomorphic sphere in X, which intersects the Lagrangian at a point here. Okay. So, right. So these are both going to be boundary points in the compactified moduli space. And so this presents right, and so this is a problem because if you want to try to define the Gromov-Witten invariance by say taking some fundamental class for this for this moduli for these moduli spaces with boundary, and then maybe intersecting them with homology classes in L and the ambient symplectic manifold to get a numerical invariant, then you're just not going to get something you're not even going to get something which is well defined because you're intersecting with a class that has boundary. And then similarly, I guess like the existence of these boundaries will also appear when you try to study the extent to which these naive invariants are well defined with respect to changes of almost complex structure. So so to get a well-defined count, you sort of need to correct this naive count of disks, this naive count of disks somehow. So there is right. So there are several ways of doing this. The one that I want to talk about today was kind of first proposed by like Joyce in 2007, and then worked out later by Fukaya and Solomon and Tukachinsky. So Fukaya kind of gave a definition of the open Gromov-Witten invariants for Maslov zero Lagrangians in Calabi-Yau threefolds, and Solomon and Tukachinsky extended it to arbitrary this definition to Lagrangian submanifolds of arbitrary dimension under some like transversality assumptions on the moduli spaces. But algebraically, the idea is that to cancel disk bubbling, so that's this kind of thing, we should equip L with a bounding cochain in the Floer complex of L, right? Where by bounding cochain I mean like the kind of thing considered by Fukaya A-infinity and Ono. So I'm now going to just try to give like a little bit of background to describe what I mean by this. So I want to let K be a field, and I will define I'll define, the Novikov ring, or I guess I guess this is like the Novikov field over K to be the set of formal sums with coefficients A sub I living in K, and and then powers of a formal variable T where, and there's a typo here, but that should say that the limit of the lambda sub i's goes to infinity. So you would use this to keep track of the areas of holomorphic disks, basically. And then this is kind of a technical point, but to account for, basically to make sure that the gradings worked correctly and to account for positive dimensional incidence constraints. What we want to do is we want to actually extend this by considering some formal variables, E, S, T, and I, which can have like non-zero integer gradings. Okay, and then finally, I want to let C star L with coefficients in R sub K denote some chain level DGA model for the ordinary cohomology of L with coefficients in R sub K. So, like I guess the three examples of this which will be relevant are we can consider the de Rham complex when K is either C or R, but then we can also consider like the complex of smooth singular chains, and then the main results of this talk are actually going to involve Morse cochains instead. But I want to for now, but I want to like for now stay, in some kind of like vague, some kind of like vague setting, because the differences at the chain level between these three models will be relevant later. So in this setting, the Fukaya A-infinity algebra of L consists of operations M sub K, which go with K inputs and one output. And these should satisfy what are called the curved A-infinity relations. So, so you look at all compositions of this form, and then, sorry, so this is another typo, but this should say that this sum should vanish here. And this is for any K tuple of elements in C star, in C star of L. And the sign here is just going to be given by the Koszul sign conventions. And the way that you want to think about this is that M sub K should count J holomorphic disks with boundary on L and K plus one boundary mark points. So in particular, we're thinking of like the first of these boundary marked points as the outputs of M sub K, and then the last K of these are going to be thought of as inputs. And in particular,
can I ask a quick question? So
yes,
this is C star, this you are defining here. Can I think that as in the Fukaya category of the atomorphism of L?
sorry.
Is that a good model to think?
Right. So this is, so what I'm describing right now is basically a way of defining like the self-Hom set of L in the Fukaya category. Yeah. So there's
Okay, thank you.
Yeah. So there's Yeah, so you can like define so you can like define the entire Fukaya category along these lines by considering immersed Lagrangians, but that's kind of more than we need for the results that I want to talk about. Okay, so in particular, like M0 can be thought of as a count of disk bubbles. So this is going to count like holomorphic disks with boundary and one marked point thought of as an output. Okay, and so something which I guess maybe you can see by writing out the by like writing out these infinity relations in for small values of k, is that M1 is actually not going to be a differential on C star of L. So it's going so like M1 squared is going to equal some expression involving M2, so it's the multiplication, and then this M0, right? So so in some sense, like M0 is sort of going to be like an obstruction to defining Floer cohomology. So to correct for this, Fukaya, Oto, and Ono introduced the notion of a bounding cochain. So this is going to be a Floer cochain B of degree 1, which should satisfy the Maurer-Cartan equation here. So what that says is that if I consider the sum of M sub k with all inputs B, then this thing should vanish. And I should also say of positive valuation, just to make sure that this sum converges, right? So the Maurer-Cartan equation makes sense. So I can consider the set of all solutions to the Maurer-Cartan equation, and I'll let M of L denote the set of bounding cochains up to gauge equivalence. So we're going to take the set of Maurer-Cartan elements and like quotient out by some relation that I'm not going to describe. But I will tell you later, I guess, kind of the main consequence of gauge equivalence that is going to be relevant for defining open Gromov-Witten invariants. Okay, and so I'll just point out that when you're given a bounding cochain, the operations MBK defined by summing over all ways of inserting powers of B into the A-infinity operations are going to define an uncurved A-infinity structure on C star of L. So that's the reason for considering elements satisfying this this constraint. All right. Now, in this setting, Fukaya and Solomon Tukachinsky.
Is the ML the cochains just what you are defining in degree 1 or in all degrees?
Is the
ML.
Sorry, is the ML
The ML is the set of bounding.
Right. So bounding cochains are degree 1 for me. And so the notation is a little bit sloppy here, but what I mean by the degree is the degree which takes into account the homological degree and the degree in this ring. Okay. So that's the reason that and so this is the reason that you get kind of meaningful invariance in dimensions like other than 3, basically. So so you can consider something which is like a sum of cochains of like arbitrary geometric degrees, but then these should be like corrected by multiples of these formal variables, right? Such that you're like summing over a degree 1 thing, right? And this is just okay. Okay, so in this setting, Fukaya and Solomon Tukachinsky define an open Gromov-Witten potential as a function from the set of bounding cochains up to gauge equivalence to R sub k. And so at the chain level, they are specifically taking C star of L to be the de Rham complex of L, tensored with R sub k. And because we're working with the de Rham complex now, k has to be equal to R or C. Okay. So what they and so specifically what they do is they define psi of B to be the sum of to be this sum. So it's this number that I'm calling m minus 1 plus the sum from k equals 0 to infinity of 1 over k plus 1 of mk of b to the power k paired with b. Right. So I should explain my notation here. Following the convention that I set up for the A-infinity algebra, n minus 1 should be a count of disks with no boundary marked points, and then this pairing here is just the Poincare, right? It's just going to be the Poincare duality pairing. So on the de Rham complex is going to be given by taking the wedge product and then integrating over L. Okay, and there's going to be independent.
I'm sorry to interrupt you.
Yeah,
L
yeah.
is the Lagrangian inside of a symplectic manifold M.
That's right.
And here you said C star, the L, and that is just the Rham complex of L, which
Yes.
seems has nothing to do with the current symplectic manifold or anything.
So the underlying vector space doesn't. The operations have like count disks in M. I see. Yeah.
I see. I see.
Yeah.
So the symplectic structure, current symplectic structure is
Right.
really depends on how the infinite structure is defined.
Right. So the Lagrangian embed. Right. So by considering like L as a Lagrangian submanifold of M and counting disks on with boundary on L inside of M, you're going to get some. Right, you're going to define some operations on the de Rham complex of L. Yeah. Right.
Okay, thank you.
Right. So it's like an extra structure like on top of this this topological thing. Okay. So the psi of B is going to be independent of J up to a count of closed curves. And the reason that it's so the reason that we have this sort of weak invariant statement is because of this like sphere bubbling phenomenon that I showed you before. So if I just try to count disks with no boundary marked points, what can happen is that as I vary J, I can see some of the boundaries of these disks collapse, and these things will become holomorphic spheres inside M. So this is right. So this is sort of just a fact of life, but the thing to do here is to say that when L is null homologous, I can, do some add some additional correction term to get an invariant. And what I should do is I should choose some like smooth singular chain whose boundary is L, and I should count disks holomorphic spheres which intersect this chain at a point. Okay. And then there's a way of showing that like this new quantity is actually like going to honestly be independent of J, right? So this is how you get like proper open Gromov-Witten invariants, but I have nothing new to say about that, so I won't elaborate too much on this. But when L is null homologous, what we can say is that we can extract the open Gromov-Witten invariants of the pair L sub B, right, which should just be the coefficients of psi B. And really the way I've set things up, they're going to depend both on like a choice of bounding chain for L and a bounding cochain in the sense of Fukaya O to Ono, but nonetheless you get some number which is independent of the almost complex structure. Okay. So there's one additional caveat here, and that's that to prove that psi of B only depends on the bounding cochain up to gauge equivalence, I want to know that the Poincare pairing is cyclically symmetric, right? So what this means is that I can take any tuple of elements, A0 through AK, and then I can look at the operation which pairs M sub K of A1 through AK with A0. And cyclic symmetry says that up to a cosine sign, this like K plus 1, this operation with K plus 1 inputs should be preserved by cyclically permuting the inputs. Okay. So, you would think that this should just come from looking at, from using like the S1 symmetry of the disk, because like really somehow this quantity on the left should just be counting disks with K plus 1 inputs and incidence conditions given by A0 through AK. So, of course, I should just be able to cyclically permute them. But actually, cyclically symmetry has only been established for the integration pairing on the de Rham complex. And this is a result of Fukaya's in 2010. And this is the reason that Fukaya's and Solomon-Tukachinsky's invariants are both only defined over fields containing the real or the complex numbers. Okay, and so the reason for this is that to actually define these A-infinity operations, you have to look at some kind of domain-dependent perturbations of the almost complex structure, okay? And, right, so in particular, like Kuranishi structures on these moduli spaces are going to be a type of domain-dependent perturbation, and it's just difficult to make sure that these things are these perturbations are actually S1 symmetric. But right, but Fukaya has but I guess Fukaya has an argument which shows that this is possible, but it involves the process of forgetting boundary marked points. So somehow you have to relate the Kuranishi structures on the space, on the moduli spaces of disks with k marked points to the Kuranishi structures on moduli spaces of disks with k-1 marked points. And if you do this, there's actually a dimension counting argument which kind of shows that these moduli spaces are, the dimensions of these moduli spaces have to grow linearly somehow as you increase the value of k, right? And so a consequence of this that I don't want to really belabor in this talk is that you can only define the A-infinity structure on the de Rham complex. So it is insufficient for getting something which is defined over singular chains, which is okay. But but I guess I'll just move on now and talk about how cyclic symmetry is actually used in this definition. And so it's So something special about working in characteristic 0 is that gauge equivalence of bounding cochains B0 and B1 implies the existence of a path of bounding cochains joining these two things. Okay, so to see that psi of B is well defined, I can consider psi of B evaluated at this at this path of bounding cochains. This is going to give me some path in T, and then I can differentiate this and with respect to T. And I want to show that this is 0. So so this derivative should not depend on m-1 because it's constant. So I'm really just differentiating the right-hand side of this equation. The derivative here is just going to be given by taking the product rule, essentially. So I differentiate each of these inputs and inside the n sub k's, and this last sum corresponds to differentiating the b sub t's in the second slot. So there are actually and so now what I want to do is I want to apply cyclic symmetry to the first summand here. So what I'm going to do is I'm going to move dbt dt into the second slot. If I do this to each of these summands, there are actually going to be k of them, which is going to leave me with this expression on the bottom line. But in the first slot here, you can see that what I have is really just a copy of the Maurer-Cartan equation. And so this is going to vanish using that the b sub t's are bounding cochains.
So in this cyclic condition, when you use, you do have the sign issues, do you?
Yes. So because we're in degree 1, the sign is actually always going to be positive here.
I see. So the dBdt is also having the same degree.
dBdt
they all
is
have
also
the same degree.
They'll all have the same degree. Yeah. So
and the B, so that's what I was going to ask.
Mm-hmm.
That the sign was depending on this degree of the complex, not the degree of the coefficient, or not.
So if you set things up correctly, the sign will also involve the degrees of the coefficients. So
that's where the plus or minus, it's kind of a more cohomological type of a sign change.
Yeah, that's right. Right. So but it will be set up so that in this example, the sign is always going to be +1, right? When you
Okay, thank you.
look at these right. Okay. So what I want to describe for you is a way of making most of the story work for coefficients, right? For coefficients that aren't the real or the complex numbers. So under some regularity assumptions on the pair ML, which I'll just say for the record now are satisfied by any monotone Lagrangian, and in all of the settings that Solomon and Tukachinsky consider, there is an open Gromov-Witten potential, which I'll denote by capital phi, with values in R sub k for any field of characteristic 0, which is which has the same invariance properties as the potential defined earlier. And if you construct phi correctly, it will also coincide with Solomon Tukachinsky's open Gromov-Witten potential when their thing is defined. So as a corollary of this, we get that if B is a bounding cochain defined over K, then the pair L comma B has open Gromov-Witten invariance valued in K. And so one like geometrically appealing consequence of this is that if I take a Lagrangian rational homology sphere, it's going to have like rational open Gromov-Witten invariance. So, in this level of generality, it's not something that you can say using Solomon and Tukachinsky or Fukaya's setup, but here if you have like control over the coefficient, basically of the coefficients over which the Fukaya category is defined, then this is a statement that you can make, and kind of the geometric input that we're using here is a result in FO cubed, which says that any Lagrangian rational homology sphere is always unobstructed in characteristic 0. Okay, and so the idea here is to consider what exactly cyclic symmetry gives you. So so if I know that the Poincare pairing is cyclically symmetric, then it's going to induce a map from A to the linear dual A check, where by A what I mean is like again C star of L, which I'm choosing to write like this because it makes the notation a little bit nicer. So on the one hand, this tells you that it's an A-infinity bimodule homomorphism, but it actually says, a little bit more. So symmetry here is actually going to translate into like some skew symmetry, where again, I'm leaving the signs unspecified. And then, because of the way that, using the fact that, that this thing is a Poincare pairing, we also know that it's homologically non-degenerate, by which I mean that for each class A in the homology of A, there's some B in the homology of A such that psi of 0 of A paired with B is non-zero. And so in the filtered case, this should really be the homology with with respect to the like de Rham differential or something, but this is sort of a minor point here. Okay, so so the basic idea here is that in an ideal world, we would like to appeal to this result of Kontsevich and Soibelman, which says that if I take an A-infinity algebra A and I have a strong proper Calabi-Yau structure on it, then it will determine a strictly cyclic pairing on some minimal model for A, right? And this result is, I should just emphasize this result is special to characteristic 0. So that's, another place where this is going to be used. So the naive thing to do here would be to, go back to the definition of the potential that I gave you, and so it would be to go back to this definition and try to phrase everything using some minimal model for this A-infinity algebra. So you could say, well, even if we don't get cyclic symmetry at the chain level, we can just pass to this minimal model where we do have cyclic symmetry and which exists by Kontsevich-Soibelman, and just define it this way. Okay. but this is maybe not such a good thing to do because, the minimal model that we choose is only going to be related to A by some, right, sort of, right, by like some sort of A-infinity homomorphism. And it actually turns out that, in the, right, like, because we're looking at like curved A-infinity algebras where M0 is potentially non-zero, something that can happen is that, is that like the higher order terms of this Gromov-Witten potential we look at can actually fail to be can actually like fail to be preserved by like A-infinity homomorphisms. Okay. So, changing our chain level model for the A-infinity algebra is actually kind of an inconvenient thing to do, right, from that perspective. So what we do, right, so what I'm going to do instead is I'm going to appeal to a result which is originally due to Cho and Lee, and then there's another version of this which is due to Amorman 2, which is to instead associate to a strong proper Calabi-Yau structure on A, what Cho and Lee called a strong homotopy inner product on A. So it's some kind of chain level version of, or like, kind of, notion of a cyclic pairing that, right, where you only have, cyclic symmetry up to homotopy. Okay. So I will try to tell you what I mean by this. So, so a strong homotopy inner product on A is an A-infinity bimodule quasi-isomorphism phi from A to the linear dual A check. But really but like in full generality, what this should actually consist of is a family of linear maps, phi sub PQ, where P and Q are both non-negative integers, which goes from A to the power of P, tensored with tensored with A to the power Q, mapping into the dual of A. And for convenience, I've underlined the factor of A, which I'm thinking of as the bimodule factor. So the two powers of A are going to, we think of these as like acting on the left and right by this. So there's going to be some family of maps, and they should satisfy the following three conditions. So the first thing is homological non-degeneracy, which is the same condition that I wrote before applied to phi 0, 0. So it should roughly say that phi 0, 0 induces a non-degenerate pairing on the homology. The second condition is going to be some kind of generalization of skew symmetry. So really here, this should be like, really here is that these should be like, on the left-hand side, you should have like P sub Q, and on the right-hand side, this should be like phi sub QP. And this just says that, and you can kind of think of this as saying that, each of these maps are, sort of invariant under some cyclic permutations. So it's really just, like, I guess like the analog of cyclic symmetry for these higher order things. Then this last condition is and this last condition is called closedness. So it says that for any like n tuple of elements x0 through xn in A, and any triple I less than j less than k between 0 and n, we have like again up to causal signs that that like this sum is 0. So so what I actually mean by this is that I just I will just like look at all cyclic permute, I guess like up to cyclically permuting my inputs. I will look at the three expressions where x sub I, where like x sub I is the bimodule element and x sub j is the input, and then so I have like the expression where xj is the bimodule element and xk is the input, and the one where xk is the bimodule element and xi is the input. And I should say that the sum of all of these things is equal to 0. Before moving on, what I'll just say is that so Kontsevich and Soibelman's result about the existence of a cyclic pairing can sort of be thought of, right, can be thought of as some kind of non-commutative Darboux theorem, right? So, so, right. So I guess like this the strictly cyclic pairing is, can be thought of as like some kind of constant symplectic form on, on a formal manifold. And what they show is that, any symplectic form can sort of be, can be made, can be like made to agree with, the standard one up to some A-infinity homomorphism, right? And so in the and so in this language, the skew symmetry condition and the closedness condition are going to correspond to like these properties for symplectic form. Okay, so in the latter cases, this is actually where the name closed comes, where the name closed comes from. It's like, closed as in a closed differential form. Okay, so and so the geometric situation that I want to consider is that I want to take C star of L with coefficients in Rk now to be the Morse complex for some Morse-Smale function L to R. Right? And so the A-infinity operations in this case are going to count pseudoholomorphic Perley trees where, and so what I really mean by this is that these are trees where the vertices are going to be labeled by like holomorphic disks, by like holomorphic disks with boundary on L, or possibly like closed holomorphic curves. And then each of these edges are going to be labeled, each of these edges are going to be labeled by like gradient flow lines of some perturbation of this Morse function, right? So, geometrically what I'll see is some collection of like disks with boundary on L, and then gradient flow lines which hit the boundary of these disks. Okay, and then the exterior edges should should kind of like terminate at the critical points of this Morse function. Okay, so analytically, this model for the Lagrangian Floer complex is sort of easier to set up than the de Rham complex, because everything is finite dimensional, but for one thing, but more importantly, you actually get to perturb this Morse function so that it, so it kind of interacts nicely with these moduli spaces of disks. Of course, if you do this, there's, kind of no reason to expect that you get something cyclically symmetric anymore, but I guess this is the advantage of using like Cho and Lee, like kind of Cho and Lee's setup. And what I'm going to assume here is that all moduli spaces of what I call pseudoholomorphic Perley trees of dimension less than or equal to 1 are cut out transversely, right? So these are like the weak regularity assumptions that I mentioned in the statement of the main theorem. But of course you could, but like, in principle, this should all be made to work like whenever the Floer complex is defined. I'll just mention for the record that the analog of m-1 that we're going to be looking at in this case is going to count trees which look like this, which have no exterior edges. Okay, so you just like, so you're going to be looking at trees like with a root. So, but like no semi-infinite edges. So there's just the kind of thing that you get by like forgetting all of the all of the exterior edges on the kind of thing that would contribute to the A-infinity operations. Okay.
You could get finite edges between two disks.
You're going to have, yes, you'll get finite edges between two disks, but you don't have like semi-infinite edges, right? And so the reason that we do this is that if you look at is if you take like the kind of thing m-1 and as I've defined it, and you like think about how it behaves as you vary the almost complex structure, the codimension one things that you can see is that you can see a finite edge, like is that you can like see one of these finite edges break into like a broken Morse flow line, or you can see some kind of disk bubble. But in either case, you're going to get like a union of like two things, which, where like one of them now looks like it should contribute to M0 because it has an output, and then one of them should look like it contributes to M0 up to kind of changing orientations on everything. So it's going to look like two copies of M0 like paired with itself somehow. But yes, you will get finite edges, which is right, which I guess on the one hand makes it difficult to compare with like other definitions of the open Gromov-Witten invariance, but it's something that's necessary because we've set everything else up involving okay, right, involving Morse theory. Okay, so I said that Cho and Lee's result is going to come from having a strong proper Calabi-Yau structure. So there's another typo for which I apologize. But I need to show you how to construct such a thing. So if I take A to be C star of L again, the strong proper Calabi-Yau structure that I'm going to consider comes from a variant of Ganatra's cyclic open closed map. So this is going to, concretely be given by a sequence of linear maps of, indexed by indexed by integers m greater than or equal to 0, which are going to map from the reduced cyclic chain complex of A to the Morse complex for the underlying symplectic manifold. So there's again a choice of Morse function which is involved here, but you can ultimately show that the invariance that you get will be independent of this thing. Okay. Right, and then the key property of these OC subs, of these OC sub M's is that they should intertwine the S1 actions. So, I mean, yeah, okay. So by S1 action, I mean a homological S1 action. So in this equation, little b is going to be the Hochschild differential on the cyclic chain complex, and b is the Cons operator. So if you haven't seen this before, this big B should square to 0. So you're so you kind of want to think of this as the action of the fundamental class of S1 on the cyclic chain complex. And then we're going to be working with the with what you can think of as a trivial S1 action on the cyclic chain complex. So in particular, everything just acts by 0, which is why the right-hand side of this equation here is going to be 0 and not some other thing. Okay. So the way to set this thing up in Morse theory is to define OC sub M as a count of Perley trees with a root labeled by a disk that looks like this. Okay. So I'm going to have, okay. So I should just explain what all of these marked points mean. So the white marked point in the center here is going to be something which I think of as an output for the Morse function, for the cyclic open closed map. So there should be a flow line of M which kind of emanates out from this and lands at some critical point of the Morse function for M. And then the white, the white marked points P1 through PM are going to be constrained to lie on circles in the domain, which are centered at this output. Okay. And and then I should also have, some boundary marked points, so that's what the ZK here is. It's one of the boundary marked points. And I guess if you want to make things fully general, what you can also do is you can you can consider some additional marked interior marked points here. So these are the blocked marked points, and these are going to take inputs from the code, from the cochain complex of M. So, this is how you get like bulk deformed versions of the open closed map, for example, but it's not right, but it's not something that you need to worry about. Okay. And then right. Right. And then kind of the way, right. And so kind of the reason that these OC sub M's should sort of give you something that right, that satisfies this relation here. Right, is because you can just take like think about where these you can just like I guess like consider I guess you can just like relate the moduli space of disks with like M auxiliary marked points to the moduli spaces with like M-1 auxiliary marked points somehow, right? So you can like forget one of these things that are constrained to lie on a circle. Okay. So you can construct such a thing following following Ganache's prescription or some like Perley version of this. So if I'm given such a thing, then there's an algebraic procedure described by Cho and Lee, which lets you associate a strong homotopy inner product to this thing. So I'll let little phi denote the strong homotopy inner product associated to Ganache's cyclic open closed map. Okay. And then in this setting, the open Gromov-Witten potential big 5b is defined to be M-1, where here this is like the Perley version of M-1 again, plus the sum from n equals 0 to infinity and the sum of non-negative integers p, q, and k, whose sum is equal to n, of things which look like this. So I see 1 over big N plus 1 times phi sub pq with inputs given by like b to the power p tensor mk of b to the power k tensored with b to the power q, right? So this thing is going to give me some element in the dual space to the A-infinity algebra, and then I'll evaluate this and then I'll like evaluate this thing in B. Okay. So in particular, if I just specialize to the case where specialize to where P and Q are both equal to 0, then I'm just going to get something which looks like the original open Gromov-Witten potential. Okay. Right. And then the last thing to say here is that now you have to show that this entire thing is sort of invariant under changes of almost complex structure. And the key fact here is that we can say that the open close is that if I look at this cyclic open close map, then the strong homotopy inner product that it induces is actually going to just descend to the Poincare pairing on the on like the ordinary cohomology of L. Okay. And this just follows from the fact that if you look at inputs of like top cohomological degree, all that you end up actually counting in the definition of this open closed map is just going to be like constant disks. So yeah. Okay. But that's all I want. But I guess that's all I wanted to say. So I'll just stop here and see if there are any questions. So thanks.
Thanks. It's right exactly at the time as the bell rang here in the department. So perfect timing. So any questions? If not, can you were you going to ask questions, Zhongzhu?
Yeah, that helps.
Okay.
So here you use the infinite forms, and Thomas Tredner did this, not of course from the Gromov-Witten theory, but purely from topological sense to deal with the Poincare duality. How is this different from what he did?
Okay, can you remind me? Can you remind me what your Tradler's results you're talking about?
Well, he defined some on the topological spaces with symplectic chains and define the infinite product.
Right.
You actually referenced the paper.
Do I refer? I don't. No,
Yes,
so
you did.
I don't reference Tradler's thing directly. Yeah. So I guess like for what? Right. So I guess like for one thing, I'm looking at I guess like Lagrangian submanifolds, which which bound holomorphic disks. So really, if you, right, so like really, if you unwind everything, this this little phi is actually going to it's actually going to involve like counts of disks somehow. So I mean, like maybe something to ask is like if you if you
Well,
work in like
he was doing it just very abstractly, so really didn't apply anything to the, as far as I quickly scanned through, to the Gromov-Witten or holomorphic disks.
Right, I actually hadn't thought about this, but like maybe something that you could say is that like if you like work in some kind of setting where you said a priori that your Lagrangian submanifold like doesn't bound any disks, like does this construction recover Tradler's thing? And I'm not I'm not sure, but that's
Yeah, in your paper, you're also having another parameter in the definition, the exponential e to the beta.
Exponential e to the beta.
Yeah, e to the exponential to the beta.
Right. So these are right. So I guess like really in the definition of the A-infinity algebra, there are like more there I guess there's like a little bit more structure here. So there is so I guess like these A-infinity operations are like further going to they're going to further decompose as like a sum over like second relative homology classes of
beta should be the homology classes. And also there's another parameter, capital T to the power.
Capital T, capital T is the Novikov variable.
Yeah, okay, that's okay. This is in the
So I've just like suppressed all of this, but I'm looking at like T to the power of like omega of a relative homology class. But if you like so like the M sub K is, so you actually get like some operation which is associated to each second relative homology class. It specifically just counts disks with like in the class beta, but if you like weight all of these by T to like the area of like to like the symplectic area of one of these classes and then sum over all of these, then you get the M sub Ks that I defined here.
So I was curious why you're in the Novikov field and you added them, and the RK actually is the formal power series ran with many variables, ES, and T1 up to Tn. So how are those variables or recording? What information do those variables record?
So the information that these okay. So I guess like I guess like the way that you so I guess like okay. So what each of these each of these variables do slightly different things. So the E variable is going to be something which corrects for disks of like non-zero Maslov index. The S variable accounts for interior constraints, and then the T sub I variable, or sorry, this is going to account for like constraints in the coming from like the homology of the Lagrangian, and the T sub i's account for constraints coming from the homology of the ambient symplectic manifold. Okay, and so like kind of the so let's just let's just think about boundary mark points for a second. So if I want to say have my bounding cochain like B involve let's just say like Morse cochains of like degree not equal to 1, then what I should do is I should multiply these classes by some power of S, which is going to like such that like S times the cycle is something of degree 1, right? And so this is going so this is like just something that I need to do if I if I want to make sure that
Okay, that makes
if I want to
sense.
make sure that my infinite algebra is still graded. Okay.
Well, thank you.
But then I can like look at the coefficient of like S
Yeah.
in like the Gromov-Witten potential, and then this should give me like the Gromov-Witten invariant with like one boundary constraint or something. Like that's kind of the idea.
Thank you.
Yeah. Okay.
Can I ask you a question about your picture with the disk with all this?
Yes.
I just wanted to ask a question about
Yeah.
that. So the W's are the kind of honest interior marked points that you want to deform by. And
Yes.
the P's are the auxiliary things.
The P's are going The P's are going to be auxiliary marked points, so they're only allowed to like. So if I so the thing to say is that if I normalize this picture so that or if I normalize this domain so that like Z sub k is at lies at like minus I and P and like P out lies at 0 in the complex plane, then these then like these dashed circles should should then correspond to like honest circles. And these dashed circles should correspond to like circles in the complex plane, and you want to say that like the P sub M should like lie on these circles. Yeah.
Okay, but they have no further restrictions. The P's.
In the definition of the map, no. I mean, you don't want yeah, I mean, like you just don't want them to like go past each other. So like PM can't be closer to the output than like P sub M minus 1.
Okay.
Yeah.
And so what happens when they kind of collide in the compactification when two circles?
Right. So yeah, I get right. So I guess So I guess like So I guess like we're So I guess two of these circles can collide in the compactification. Then you're going to get like so you're like still going to be like see like some sphere bubble when this happens. But this is something that's going to happen, that's only going to happen in codimension 2. So when you when you try to prove this relation for like relating like OCM minus 1 to OCM, you're actually only going to be looking at codimension 1 strata in this moduli space. So so I guess like if you so I guess like the thing to say is that if you like choose your Morse function, like generically you can you can assume that you actually never see these strata where where these like two boundary marked where these like auxiliary interior marked points coincide.
But they could have the same modulus, right? That's codimension 1.
Sorry. No, sorry. So in the moduli space we're looking at, we're just like assuming, we're like adding the constraint that these moduluses are like strictly increasing. Sorry.
Okay, but in the compactification, don't you have the case where they kind of
yeah. So
on top of the same circle?
Yeah. In the yeah. So in the So in the So in the compactification, they can't coincide. So you will like see such things when you so they will so if I remember correctly, you will see such things when you try to prove that that this relation is satisfied, but when they coincide with each other, there's going to be some kind of procedure for forgetting for forgetting one of these for forgetting one of these interior mark points. So in that way you and so like that's what I meant when you said you relate the moduli spaces of like M minus 1 marked points with the one with M auxiliary marked points. Yeah.
Okay.
Yeah.
Thank you.
Sorry if that was unclear.
That's okay. Any other questions before we go? No? Okay, so thanks a lot, Sebastian,
Mhm.
for the talk. And that's it for today.
Thank you.